Okay, so I guess we can start. So it's really my pleasure to introduce Pieter Velbeke. So Pieter got his PhD at Ghent University in the Department of Experimental Psychology in the group of Professor Tom Vergoet, which is a group that's mainly focusing on doing computational cognitive neuroscience. And so Pieter actually did this pretty amazing PhD, and I was lucky enough to attend his defense. And he was working on these very nice oscillatory neural networks, trying to combine concepts like binding by synchrony, communication through coherence, and reinforcement learning in order to understand basically how you can kind of orthogonalize stimulus response representations. And these models were very nice because they make pretty, given that they're oscillatory models, they can make these very nice concrete predictions regarding what you would observe in the brain, and specifically within time frequency kind of data, EEG data. And so they did that, and they observed basically the predictions that they had in cognitive control tasks. And so I really encourage everybody to go and have a look at his kind of earlier work. It's really cool stuff. But today he's going to be more talking about this notion of how you have to optimally balance shared versus separated representations in order to really tackle this continual learning issue. And so apart from all of this amazing work that he's been doing, he's really a very nice person overall, and also very willing to collaborate and always giving super nice feedback during the lab meetings. I remember we were colleagues for a while. So yeah, just like take it away, Pieter. Thank you again for presenting here.
Okay, thanks a lot, Chris, for this nice words. So yeah, I will indeed present some work that we did on continual learning. Some work will be from my PhD, some work from after it. And for this presentation, I try to focus on the computational work that I have done. But as Chris said, I'm from a psychology department, and our main question is how humans do continual learning. So there will also be some empirical work with a link to neuroscience. Yes. So we started from the fact that humans exhibit lifelong learning for an unbelievable number of complex tasks. And in artificial neural networks, there are basically two problems for this continual learning. One is catastrophic interference. I guess most of you know it, where neural networks tend to override or forget previous knowledge. So there's basically a need to separate information according to the two tasks. Another challenge is generalization, because in artificial networks, they cannot always appropriately generalize information from all tasks to speed up learning in the new task. So there's also a need to share information across tasks. And this is a bit a balance that they need to find. So in my PhD, I mainly focused on the catastrophic interference parts, where we want to separate task representations. So here, consider this example of Belgium, which is divided in two parts, Dutch-speaking and a French-speaking part. And usually we have one native language, and then at the age of like 12 years old or so, we start learning the other language at school. Now, for classic networks, this would, of course, be very problematic, since it would have the tendency to override the first learned language, so the native language, with that new language. And our solution is very straightforward. We just separate the two tasks in two neural modules. But of course, then the question is how activity flow through each module is mechanistically guided. And for this, we rely on a theory in neuroscience, which is the binding by synchrony theory, which argues that neural activity basically oscillates. So it has this wave-like pattern, and that neurons that oscillate in synchrony are communicating, while neurons that are oscillating out of synchrony do not communicate. Hence, the only thing that the agent has to do to speak and learn French without overwriting Dutch is to synchronize oscillations in that module with in that French module with the input and output layers. So the idea is that if the model is not synchronized with the input and response, it is not active at the same time. And as a result, it will also not learn and is protected from interference. Then the question is, how does this network decide which module to use? And for this purpose, we implemented a higher level reinforcement learning system, which adaptively decides when the network should switch to another module. Basically, the system learns an expected reward for each module. And at the beginning of the learning process, the expectation of speaking French correctly will, of course, be very low, but after a while, this will increase. And then based on this expectation of reward or the expectation of doing the task correctly, the agents will accumulate evidence to switch to another module or stay with the current module. And the idea is, of course, that if the agent is receiving considerably less rewards than expected, so a negative prediction error, then the evidence to switch will increase. And when it hits the bounds, the model will switch, and instead of synchronizing the French, it will synchronize the Dutch one. So very straightforward, I guess. Yeah. Also, if there are more than 2 modules in the model, it will basically choose a module at random with the limitation to not return to the previous chosen one. So to test this network, we did not use languages, but we used a simple classification task in psychology literature known as the Wisconsin card sorting task, where the agent has to learn a mapping between a shape, for example, here is a shape and let's say a card deck. To avoid confusion, this input layer does not encode images, but just has one hot encoding, so 100 if it's a square. And there are 3 orthogonal task rules, A, B, and C, in which the mappings between the shape and the card deck changes. So in rule A, for example, shape 1 should go on card deck 2, shape 2 on card deck 2, and for rule B, shape 1 should go on card deck 3, and so on. Okay, and in separate simulations, then we also increase the dimensionality of this input space. So then you could have 2-dimensional stimuli where you have shape and color, and the Q is telling the agent whether he should classify based on the shape or based on the color. And then there was also another simulation where we performed a 3rd stimulus dimension. Yeah. The network is then trained blockwise for a fixed amount of trials, with each task being repeated twice. So there are 6 blocks, A, B, C, A, B, C, and we simulated different learning rates. And then we evaluated the model on overall accuracy across all 6 blocks, so 2 times the 3 task rules, on stability, where it forgets. So basically, whether there's catastrophic interference, where it forgets by learning the other 2 task rules in between. So we subtract the accuracy of this last period of the first occurrence of the task rule with the first few trials on the second occurrence of the task rule. If this is negative, then there is interference. And we also evaluated plasticity in the sense of how fast does it learn a new task rule. So here we show accuracy, plasticity, and stability results in different columns. And for the task with the different input dimensions, so 1 input, 2 input dimensions, 3 input dimensions, we show results for the sync model. So for our model that's divided tasks in separate modules in blue, and for a classic network that did not do this in orange. And the x-axis represents different learning rates that were used for simulations. And what we observed is that the sync model has an advantage over the classic model if there are at least 2 input dimensions. So you can clearly see that the advantage increases for 2 to 3 input dimensions. And this advantage is present for overall accuracy, plasticity, and stability. And the lack of advantage for this first one-dimensional task is due to the fact actually that task rules there are so easy that it can be learned very quickly. So forgetting is, in a sense, not really catastrophic there, because it can relearn the task so fast. And here, this higher level learning system that we have in the sync model actually slows the sync model down a bit, since it needs a couple of trials to accumulate switch evidence. Separating tasks in different modules has a computational advantage, but as psychologists, we are interested in the fact whether humans use this modularity. And we tested this with a probabilistic reversal learning task. So in this task, the participants sees either a horizontal or a vertical grading, and they have to press a button, and then based on feedback, they have to learn a rule. For example, if it's horizontal, press left, and if it's vertical, press right. But crucially, feedback is probabilistic in the sense that if you are correct, you have 80% chance of actually getting the 10 points, while if you're incorrect, you also have 20% chance of getting the 10 points. And then on certain points during the task, the rule will basically reverse. So now they have to, so there will be this dynamic in the reward for left response when you see horizontal. So basically, while you first has to press press left after horizontal stimulus, you now have to press right. And this changes a couple of times during the task. And so we are interested in whether humans are constantly relearning these mappings, or whether they use this modularity and are switching between the modules as they do in the sync model. And to test whether these modules are actually gated by synchronization, we also recorded like neural activity with EEG. So here we attach electrodes to the scalp of the participants, and we record electrical brain activity. So we asked ourselves which model describes the human behavioral data best, the classic or our sync model. And what we see here is a bit mixed evidence with a slight advantage for the classic model. But when we investigated this in more detail, we saw clear individual differences in the sense that there was a group of participants where the evidence for the sync model was really high, a group of participants where there was low evidence for the sync model, so high evidence for the classic model, and a group of participants which did not allow us to distinguish between these models. And interestingly, we also saw that the participants that fitted best with the sync model had a lower accuracy on the overall task. But given our simulations, this might not be very surprising, since basically the input was one-dimensional, and we showed in our simulations that the classic model will outperform the sync model in these situations. And then I will not go into detail about the neural data, but I just want to show you that our model simulations can provide predictions for neural data, for instance, about the amplitude and the theta frequency, depending on the prediction error of the participants. If we simulate the model, it shows clearly this pattern. And then if we look at the experimental data, we can almost see the exact same pattern. Interestingly, we also saw, if we plotted it for the different groups separately, that the group that fitted best with the sync model shows here the steepest decrease as was predicted by the model. But basically after the study, I had the feeling that we did not really answer the question whether humans use task separation or modularity during learning. And I took a step back, basically. My reasoning was that I built a computational model to solve a computational problem, but I did not build it up based on the empirical data that we have on humans. So this is what I did now. And I started from the classic Ruscola-Wagner rule with a softmax response selection. So here the expected reward for a given stimulus action mapping is updated on every trial by a factor which is proportional to their learning rate and the prediction error. And then this expected reward is used to select an action where there is a temperature parameter which determines how greedy this action selection is. So then I tried also to explore a very common computational feature that is used in human computational research, which is an adaptive learning rate. So here the idea is that the learning rate decreases once learning has converged. So once the prediction errors are very small, but speeds up again if there are strong prediction errors, because this means that probably something has changed in the environment and we need to start learning again. Then I also explored, of course, the modular switch accumulation that we have in the sync model, together with a higher level learning that I also described in the sync model. So I started from a classic Rescorla-Wagner learning model with softmax response selection, where I used experimental data to basically inform me whether an adaptive learning rate or switch accumulation or higher level learning should be implemented. So based on this, I could define 6 possible models: classic Rescorla-Wagner model, Rescorla-Wagner model with an adaptive learning rate, or with modularity, or with adaptive learning rate and modularity, with higher level learning and modularity, or with all parameters. So here in the table, if it says that the parameter is free, that means that we estimated based on the empirical data, and otherwise it was just fixed to 0, which means that this parameter was irrelevant for model behavior. Yeah. And then, of course, we want to know, before we test these models on empirical data, whether it's possible to identify which model produced the data. So in other words, if we simulate a data set with a given model and we fit all models on the output of that simulation, do we find the highest evidence for the model that produced this data? So what you want is that this diagonal is red, basically. And this indeed seems to be sort of the case. And we see that with more parameters, this identification gets better, probably because the model has a more distinct signature. And then we fitted these models on a wide variety of data sets on reversal reinforcement learning tasks. So human performing on the reinforcement learning tasks with different reward structure. Here there could be like a stable rewards probability for a given stimulus action pair, or there could be reversals, as in the task that I discussed before, or the reward probability could change in like very small steps. And across data sets, the reward probability, so for example, in the stable task, it could be like 70% for a correct response, or it could be hundreds. There was a range. Yeah, we gathered some data by contacting authors or via the open science framework. And yeah, this spanned different reward structures and reward probabilities. And then we fitted all models on all data sets and looked at the evidence for each model. And which we considered log likelihoods, which does not penalize the number of parameters in the model, but also AIC and BIC, which have penalties for highly parameterized models. And we basically see that for the stable reward structure, the Rescorla-Wagner model is the best fit. Definitely if you are looking with high penalty for the number of parameters. But for more complex reward structure, also more complex models will start to fit better. Especially the models that have built-in modularity, so the mods, higher mods, LR mods, full, these are getting increasing evidence for like these reversal learning tasks. And then when we perform regression for model features across data sets, we indeed observed that there is no evidence for one of the features in stable. So the red is evidence for models that did not have this feature. Green is for models that do have this feature. And in stable reward structures, there is almost always more evidence if the feature is not present. But in reversal learning tasks, we see a clear benefit for modularity and also for hierarchical learning. And in stepwise tasks, then there is no clear evidence for or against these features. So to basically sum up this first part, we saw that forgetting is only catastrophic for complex tasks, and that humans do use separated representations, but only if task rules are clearly orthogonal, such as in reversal learning tasks. And this might, of course, be because there is also merit in sharing representations across tasks or environments, because that allows for generalization. When we look at the world that we live in, there is a clear structure with differences and commonalities across contexts. For in this instance, in this map, we see that home prices are considerably higher along the coast of the USA. And this finding seems to generalize to, for example, gas prices, which are also higher along the coast. I do not know the underlying reason, but when looking at these maps on Google, I saw that the structure even generalizes to much less rated items, such as marijuana legalization, and apparently even the favorite soccer player. I cannot say what specifically, but there is a clearly a shared latent factor between USA coast states and that is not shared with mid-USA states. So this means that if new information is added, let's say the favorite food in California is chili con carne, I might think that this will be the case for all states along the USA's coast, but probably not in mid-USA. This is generalization, basically. So the classic framework to explain this type of generalization is clustering context in discrete states, such as in the Chinese restaurant process. So you would basically cluster similar context to the same cluster. For example, one cluster for states along the USA coast and one for mid-USA. And then you will learn knowledge for each state. Favorite soccer player is Messi, costs are high, stuff like that, and which basically means that information that is added to set A will immediately be added to both contexts that are associated with that set. So you have generalization. But of course, when we look at these maps, we see that contexts are rarely completely the same or different across all domains. And this raises the question of what the appropriate level of clustering is. For example, it's clear that we cannot generalize everything along the whole USA coasts. That might be inappropriate in some situations. So maybe we should make separate domains of knowledge, for example, for ideology about marijuana legalization and economics of the costs of the house. But of course, then if we separate too much, there is no generalization anymore. So there's a clear trade-off between generalization and interference, or between sharing and separating. And the question is whether we can find a balance between these two. And also, what about anti-correlations, right? Because contexts that are not the same are therefore not independent. Because if marijuana is legal along the coast of the USA, it's not in mid-USA. If Messi is a favorite player along the coast, it's not in mid-USA. So there's a clear anti-correlation there as well. So our idea is to move away from this discrete clustering and discrete separation or sharing and back to classic artificial networks. Because in artificial networks, contexts are usually implemented via a top-down modulation signal, which allows for a wide range of partial overlap between contexts, as well as anti-correlations, because weights could be negative or positive, right? However, we know that there is a tendency to overly share task representations, which favors generalization, but introduces catastrophic interference, especially in blocked learning. There we can clearly see a difference between interference in humans and in artificial neural networks. However, in recent work, I've shown that simple tricks can block this tendency to overly share task representations. Here we explored the nature of top-down modulation signals. These signals could be additive, as they are usually implemented, or it could be multiplicative in the sense that a transformation of the stimulus input is multiplied with the transformation of the task input. I will not discuss specific transformation here, but I tested a wide range in the paper. You can go check it. And this multiplicative modulation is computationally very similar to our sync model, basically, where syncing would mean multiplying with 1 and desyncing would mean multiplying with 0. And there is also this work from Massa et al. In PNAS, which illustrated how random multiplicative modulation signals combined with elastic rate consolidation allows to avoid catastrophic forgetting. Here we did not use elastic rate consolidation, but we let the task signals, so these mappings, be learned. And we used the MNIST dataset for this task with 1 output neurons, so just a yes or no classification task. And there were multiple tasks, such as, for example, say whether the digit is odd, even, bigger than 5, smaller than 5, bigger than 3, smaller than 7. So here we don't only have orthogonal tasks anymore, but we also have like intermediate tasks. And so the network is then trained blockwise for 3 repetitions on each task, after which rates are frozen and the network is tested again on all tasks. And what we see is that the multiplicative modulation, so the blue and yellow one, outperform additive modulation, so red and black. And it's slightly better if the modulation signals are learned. And this is, of course, because additive modulation will, as we can see here, learn or share task representations and hence experience catastrophic forgetting because it doesn't distinguish between the different tasks. While multiplicative modulation will separate all different tasks, but adding learning to this multiplicative signal will allow to find a clear structure in the task. Here you can clearly see this odd even dimension and the bigger than, smaller than dimension. And we also investigated whether it matters where modulation is applied, like on the first layer, second hidden layer, or on both. And for accuracy, it doesn't seem to matter that much. However, applying modulation at the second layer has interesting properties when thinking about humans. So this is data from some novel simulations, so the tasks are a little bit different. But the interesting part is that only applying top-down modulation at the second hidden layer will allow to create 2 types of representation: stimulus-specific representation. So here you have a representation for each digit that is shared across all tasks, and task-specific representations after modulation then. So here it's clearly grouped per task. And in humans, it is observed that they experience less catastrophic forgetting if they have a clear representation about the stimulus space. So I guess we should also further investigate whether or how this changes model behavior. Still, I did not really show whether a network can generalize to novel situations, right? And that in contrast to the Chinese restaurant process, it can do this for fully correlated contexts, partially correlated contexts, and even anti-correlated contexts. So I performed some novel simulations where we have 5 contexts, where some contexts are fully correlated. So 1 and 3 or both, they are different neurons in the task layer with 1 hot encoding, but they have the same mappings, basically the same task rule. Context 1 and 2, odds and bigger than 5, they have no correlation. Context 2 and 4, bigger than 5 or bigger than true, they have some correlation. And odd and even, they are of course anti-correlated. So I have this range of correlation between task rules. And now I want to check whether it can find the structure and use it to generalize. So the simulations consist of 4 stages. First is an initial learning stage where it learns on all these 5 contexts and on a subset of digits, so 0, 3, 4, 5, 7, and 8. Then I test it, I freeze the weights, I test on all contexts on the same digits, but of course, different instances of these digits. Then there is a generalization training stage where I let the network learn in context 1 and 2, so on odd and bigger than 5, on the leftover digits, the left out digits. And then I again freeze the weights and now tests on different instances of these digits in the remaining contexts. And what we see is that indeed, in contrast to no modulation or additive modulation, the multiplicative modulation allows for generalization in the sense that it will learn a lot faster, and it can, especially here, generalize to stimuli that it actually never experienced in that particular context. It reaches an accuracy of like 90%, while it's trained on tests data for 95% accuracy. So it has a very good generalization. So the take home here is that multiplicative modulation instead of additive will allow a network to clearly balance shared versus separated task representation. And this eliminates catastrophic forgetting and also allows for a good generalization to novel situations. However, then I come to the parts for future work. There is a clear limitation for the current network. Although it learns faster, it cannot do few-shot learning, specifically when two tasks are completely correlated, such as the two contexts that are both even classification tasks. They need to basically learn the exact same weight matrix to all hidden neurons, depending on the size of your hidden layer. That can be quite a matrix. So a lot of experience in both tasks is needed before information can be generalized. So our idea was to basically combine artificial neural networks with this idea of hierarchical higher task clustering from the Chinese restaurant process. And that this would help to detect task relations quicker and implement faster generalization, so few-shot learning. So this would be our proposal for a novel network, which I still have to implement. So it has this, again, this context and hidden layers, but now there is clustering in a task set layer. And at this layer, we would use a softmax activation rule, which would allow to use discrete clustering if this is necessary, but it does not need to be discrete, of course. And then the future goal is also to test generalization on humans. They sadly can already classify handwritten digits, so we have to come up with some other task. And here, for example, it's a task that is used by a colleague of mine. We have 8 contexts, which are locations in the sea around this group of islands, and a boat, I don't know if you see it, but the boat will bring participants to one of the locations. And once they arrived, the next screen appears, and this shows the map with a red dot of where they are, and an animal that they have to catch. And there is a cage here, which they can move with their mouse, and they have to drop the cage at the location where they think the animal is hiding. Once they drop the cage, the animal appears and basically provides feedback of where it was hiding. And in total, there are 6 sea animals, which are always hiding at the same location within a context, but at different locations across contexts. So as shown here, so the color indicates the location. And what you can see is that we again have then full correlation. For example, context 1 and 2 are completely the same. Also anti-correlation in the sense that context 1 and 2 are completely anti-correlated to 7 and 8, and we have some partial correlations in the middle. And then we would test generalization by introducing 2 new animals, and we would train them on 2 of the contexts. And then after this, we would test them without feedback, of course, so that training is stopped on all contexts for these 2 fish, and they should basically be able to appropriately generalize and catch all fish. And based on the locations where they drop the cage across stimuli and across context, we can based on their responses, see how they cluster context, in the sense that an optimal participant would show this kind of matrix where he drops the distance of dropping the location in context 1 is 0 to context 2, but is very high to context 8, and so on. So then I would like to thank you for listening, and my collaborators for helping me do this research.
Thank you, Peter. That was super cool. No sé bueno, si quieren hacer preguntas en español o en inglés, lo que quieran. Si lo hacen en español, puedo tratar de traducirla. Si no, en inglés nomás. No sé si en el chat del Zoom o si quieren hablar, pueden darle nomás. No sé si hay preguntas, en verdad. Yeah.
I have a question.
Go ahead.
Doctor, do you see in your in this field what is the closest industrial application that you can see in the research that you are taking forward?
I guess the closest one is that, of course, it can inform artificial intelligence research if you know more about human cognition. So in that aspect, you can make artificial intelligence systems for industry, right?
All right, thank you.
Yeah, I have tons of questions, Peter, but I'm just going to ask a few. Maybe one clarification question was when you said that the learn multiplicative weights were able to generalize quicker, if I understand correctly. And you said something about stimuli that it had never seen. Is it stimuli that it had never seen, or novel task and the same stimuli? So for instance, if I understood correctly, well, probably didn't understand it correctly, but my question is, so there's a task that you could think of, which is like, say if this digit is bigger than 5, right?
Mm-hmm.
And that can actually incorporate another task that is, say this digit is bigger than 6, right? But it's a different task technically, right? But yeah, you should be able to generalize very quickly because you already have that information in the task. Say this is bigger than 5, right? So my question is, when you're showing those graphs in the slide that follows, my question is it that type of generalization that it's best at, or is it just completely different and I just misunderstood, and you could clarify that for me, please?
Yeah. So I guess this page should somehow summarize it a bit. So, but the idea is that it has never seen digits 1, 2, 6, or 9 in contexts 3, 4, and 5. So basically, well, it has never learned that 6 is bigger than 3. It knows that it's bigger than 3 because it's bigger than 5. Or it has never learned that that 6 is even, but it knows because that it's even because it's not odd.
Okay. So that's basically okay. So I now I understand. Okay, so it's just a novel task basically, but that kind of, yeah. So it's like deductive, reasoning, so to speak.
Yes.
Okay, cool. The other question I had was, when I see those data that, well, I've seen them before, but when I see that the learn multiplicative, kind of network does orthogonalize representation just as much as the non-learn one, but at least it's structured in a way that it's completely orthogonal, in the sense that you see that odd is in the opposite position as even. I think that's just super cool as a finding. And what interests me there is, so you look, most of the time you look in activation space, right? So what you're plotting there is activation space, I guess. And I was wondering whether you've looked at the trajectories in weight space, in the sense that there's probably an optimal, it's taking some type of optimal trajectory to get at that solution. And the interesting thing here is, how can you speed up that trajectory? Like, what type of learning rule could you implement such that that trajectory actually is done faster than with whatever learning rule you're using in the moment, right? So I was wondering if you guys ever thought of that with Tom. Like, is there maybe a better way or maybe a better way to find a solution in the weight space?
Yeah.
I'm asking you because these are things that we've been actually always discussing with Daniel Scott from Michael Frank's lab, and like everybody looks at activation space and nobody really cares about the trajectories in weight space. Or at least I haven't seen that much work in with that respect. So I was wondering if you guys have thought of that.
So yeah, we didn't consider actual learning rules for that matter, but like because we saw the work of Timo Flesch, we also thought about rich and lazy learning. And then basically he showed that there is less catastrophic interference if you have rich learning. While here, especially for these top-down modulation signals, if it's multiplicative, it's easy if it's best if it's lazy learning. In the sense that you start from the random multiplicative and then you just do a bit of structuring this. So do I have it here? So you basically start from this and then you kind of structure it a bit.
Yeah.
So there are definitely things that would speed it up or slow it down, but we didn't consider learning rules at the moment. Okay,
cool. And I had one last question / it's like a common question. So the last proposal that you make, like the last network where you hierarchically impose a CRP on your neural network, I think that's super interesting because it does make sense, like to have some form of symbolic representation that tells you, well, look, this is from this context and this is from that context and so forth. And you project it in a way that you kind of soft max it so that you can get some type of shared context representation, I guess you can call it. And then the thing that when I see that is that although that's going to allow you to do few shot generalization, it's not going to allow you to do zero shot generalization, right? And I was again looking at that talk from Mohammedi El Gabi, that where the rats, they learn this sequence, and then you put them in a completely new environment. I mean, spatially it's the same environment, but the position of the sequence, the ABCD, completely changes, and they do it in like zero shot. They directly understand that when they get to D, they have to come back to A, which is basically the abstract structure. So I'm wondering how this type of approaches using like CRP stuff, which actually Rex Liu is going to present next week, and he also uses this type of approaches. Like I was always wondering how they can get at zero shot learning, because basically you still have to understand more or less that you have to kind of associate this type of thing, and it's hard to do it in a zero shot learning way, right?
Yeah, but I guess that's in that respect, it's really pinpoints to this learning about the stimulus space, right? Learning that, and that's indeed like I can implement it in the model here, but it doesn't seem to do anything for the behavior. So that's certainly something that we have to investigate more. But yeah, it should abstract context, but it should also learn to abstract stimulus relations, right?
Yeah. And I'm going to shoot one last question. So this kind of top-down multiplicative, learn multiplicative weights approach.
Mhm.
Do you think, like, if you take, for instance, like a deep Q network that learns a bunch of Atari games, and the Atari games themselves have like very similar structures, right? So for instance, if you take, I don't remember what the name of it exactly, Frostbite, like you take Frostbite and you have to jump from one square to another to get at a goal. And then you take another one where instead of like, if you look at Frostbite, it's like kind of more horizontally kind of shaped. But if you look at another one, you would jump like more vertically, but the idea is the same basically, right? So I'm wondering if you implement top-down modulations in a deep Q network, this kind of multiplicative ones, whether if you change the game, you would actually accelerate generalization or like task performance in that novel game. Do you think so? My point is, like, do you think this scales up to like this more complex tasks?
Yeah, of course, the only way to know is to test it, right? But yeah, I would say that's really a general principle that should get you pretty far. I'm actually very amazed myself how far, like, I didn't really expect it to do the generalization so good, but yeah, apparently it does.
I mean, that's a really cool finding that you get in this work. Yeah. Okay. So I don't know if anybody else has a question in the chat. Nobody? All right, cool. So Pieter, thanks again for accepting to give a talk at the center, and good luck on the postdoctoral fellowship project.